October 15, 1958. Inside a classified research facility in Moscow, Soviet missile engineer Gennady Sokolovsky unwrapped a wooden crate shipped from Beijing. Inside lay America's latest weapon, the one that had just changed the balance of power over the Taiwan Strait. His first reaction was laughter. The evidence seemed obvious. A lead sulfide detector from the 1940s. Simple nitrogen cooling. Only 14 vacuum tubes compared to Soviet systems using over 200 components, 5 inches in diameter, impossibly small for a guided missile. Soviet doctrine was clear. Sophisticated weapons required complex systems. Their own missiles weighed 460 pounds and cost 50,000 rubles each. This American device looked like it was assembled from spare parts in someone's garage. But the combat reports from China told a different story. 4 American fighters had engaged 126 Chinese aircraft, 6 missiles fired, 4 confirmed kills at 40,000 feet, higher than the firing aircraft could even fly. No radar guidance from the ground, no radio chatter, no human control whatsoever. The primitive American missile was hunting and killing targets completely on its own. Soviet engineers had just discovered that sometimes the most dangerous technology looks the most simple. If you value forgotten history, make sure to subscribe. We've got more documented accounts worth discovering. Comment your city and local time below. The metallic clang of the crowbar against Russian pine echoed through the sterile corridors of TCGI as Gennady Sokolovsky pried open the final wooden slat. Steam rose from the dry ice packed around the weapon, creating ghostly tendrils in the fluorescent lighting of Laboratory 7. 3 weeks had passed since Chinese intelligence officers had carefully extracted this prize from the fuselage of a damaged MiG-17, and now it lay before the Soviet Union's most senior missile engineer like an archaeological artifact from a technologically primitive civilization. Sokolovsky lifted the device with both hands, surprised by its lightness. At 91 pounds, the American AIM-9 Sidewinder weighed less than half of what Soviet doctrine considered the minimum for an effective guided weapon. The missile's cylindrical body, painted in standard U.S. Navy white with black markings, measured exactly 9 feet in length, dimensions that violated everything Sokolovsky understood about modern warfare. His team's latest creation, the K-5 Alkali, stretched nearly 12 feet and required a massive ground-based radar system to guide it to target. This American contraption appeared designed by engineers who had never studied proper missile architecture. The nose cone drew Sokolovsky's immediate attention. Instead of the hardened steel radar dome he expected, the Americans had installed what appeared to be ordinary glass. He tapped it gently with his knuckle, producing a hollow ring that confirmed his suspicions. Fragile, impractical, obviously inferior to Soviet titanium construction. Behind the transparent dome sat a peculiar mechanism, a mirror mounted on gimbals spinning at what his calculation suggested was several thousand revolutions per minute. The entire assembly looked like something from a university physics laboratory rather than a combat weapon. Vladimir Zvagintsev, his chief metallurgist, approached with a magnifying glass and began examining the missile's external components. "Comrade Sokolovsky," he called out, his voice carrying a note of professional confusion, "the manufacturing tolerances are extraordinary. These aluminum fins show machining precision to within 0.002 of an inch. But look at these tiny wheels attached to the control surfaces. They appear to be functioning gyroscopes." Sokolovsky moved to examine what Zvagintsev had discovered. 4 miniature wheels, each no larger than a coin, were mounted on the missile's tail fins. American technical documentation captured along with the weapon referred to these devices as rollerons, a term that appeared nowhere in Soviet engineering literature. The concept seemed absurd, using spinning wheels to control a supersonic projectile. Soviet missiles employed sophisticated electronic guidance systems and hydraulic actuators. These Americans had apparently chosen to rely on children's toys. The intelligence briefing folder contained 43 pages of combat reports from the September engagement over the Taiwan Strait. Sokolovsky spread the documents across his laboratory bench, searching for evidence that would explain how such a primitive weapon had achieved the reported performance statistics. The numbers defied rational analysis. Taiwanese pilots flying American-supplied F-86F Sabres had engaged a formation of Chinese MiG-17Fs at an altitude of 40,000 feet, 3,000 feet higher than the F-86's operational ceiling, according to Soviet intelligence files. The engagement had lasted 7 minutes. American pilots had fired 6 Sidewinder missiles and achieved 4 confirmed kills. The mathematical implications staggered Sokolovsky. A hit probability of 67% using a weapon that appeared to have been assembled from commercial electronics parts. Soviet air-to-air missiles, products of the world's most advanced aeronautical research institutes, achieved hit probabilities of approximately 30% under optimal conditions. Gun camera footage from the engagement provided the most disturbing evidence. Sokolovsky threaded the film into a 16mm projector and watched grainy black and white images of Chinese aircraft exploding in midair. The Sidewinder missiles visible in the footage moved with impossible precision, adjusting their flight paths to intercept maneuvering targets with mechanical perfection. No radio guidance, no ground control, no human intervention whatsoever. The final frame showed something that challenged every assumption about missile technology: an American Sidewinder pursuing a Chinese MiG through a steep climbing turn, maintaining perfect intercept geometry despite the target's desperate evasive maneuvers. The missile's trajectory displayed characteristics that Soviet engineers associated only with beam-riding weapons requiring constant guidance updates from ground stations. Yet intelligence reports confirmed that American pilots had simply pointed their aircraft at enemy targets, heard an audio tone through their headphones, and squeezed their triggers. Sokolovsky rewound the film and watched the sequence again. The American missile appeared to think independently, making guidance corrections faster than any human operator could react. Soviet doctrine required elaborate ground-based radar installations to achieve similar performance. The implications were strategically catastrophic. American fighters could engage Soviet aircraft without revealing the locations of supporting radar systems. They could operate independently, beyond the range of ground control, carrying weapons that functioned as autonomous hunters. By evening, Sokolovsky had compiled his preliminary assessment in a classified memorandum destined for the highest levels of Soviet leadership. His technical evaluation filled 18 pages, but the essential conclusion could be summarized in a single sentence. American engineers had achieved breakthrough performance using technology that appeared primitive only because it represented a completely different approach to the fundamental problem of guided missile design. The final paragraph of his report would later be declassified during the 1990s, revealing the moment when Soviet confidence first cracked. Recommend immediate priority reverse engineering program. American Sidewinder missile demonstrates autonomous guidance capability beyond current Soviet systems. Estimated development timeline: 24 months for functional prototype. Request unlimited funding authorization and access to specialized electronics manufacturing facilities. 3 days later, a courier delivered Sokolovsky's new orders in a sealed envelope marked with the highest security classification. The message was brief and unambiguous. Comrade Sokolovsky, you will reverse engineer this American device. You have 2 years. 9 years earlier, in the sweltering heat of California's Mojave Desert, William McLean had stared at the same fundamental problem that now consumed Gennady Sokolovsky's attention in Moscow. The Naval Ordnance Test Station at China Lake sprawled across 1,100 square miles of barren landscape, its laboratories and testing ranges hidden from civilian view by mountains and military secrecy. McLean, the son of a Presbyterian minister from Montana, had arrived at this remote installation in 1945 with a physics doctorate and an unconventional approach to engineering problems that his colleagues initially dismissed as academic theorizing. The breakthrough had occurred on a Tuesday morning in March of 1949. McLean stood before a blackboard covered with trajectory calculations, surrounded by a team of younger engineers who had grown accustomed to their supervisor's habit of questioning fundamental assumptions about weapons design. The problem they faced was straightforward in concept, but seemingly impossible in execution: how to build a missile that could hunt and kill enemy aircraft without requiring guidance from ground-based radar stations. Existing American air-to-air missiles followed Soviet design philosophy, relying on radar beam riding systems that required pilots to maintain constant radio contact with ground controllers. The process was cumbersome, vulnerable to electronic jamming, and tactically limiting. Pilots became sitting targets while waiting for guidance updates from operators who might be hundreds of miles away. McLean's revolutionary insight emerged from a simple question that had never been asked. What if missiles didn't need human guidance at all? The concept that would eventually become the Sidewinder began with McLean's observation of rattlesnakes hunting mice in the desert surrounding China Lake. These predators used heat-sensing organs to track warm-blooded prey in complete darkness, demonstrating that infrared detection could provide precise targeting information without radio signals or radar emissions. McLean spent weeks in the technical library researching infrared physics and heat detection mechanisms, gradually developing the theoretical framework for an autonomous missile guidance system. The engineering challenges were staggering. Infrared detectors in 1949 required cooling to temperatures approaching absolute zero to function with any reliability. The most sensitive available technology used lead sulfide crystals that produced electrical signals when exposed to heat radiation, but these devices operated effectively only when cooled to minus 80 degrees Fahrenheit. McLean's team would need to design a cooling system that could maintain Arctic temperatures inside a missile traveling at twice the speed of sound through desert air heated to over 100 degrees. More fundamentally, they needed to solve the problem of autonomous guidance without computers. Electronic calculating machines in 1949 occupied entire rooms and required teams of operators to function. McLean's missile would need to perform complex mathematical calculations using analog circuits small enough to fit inside a 5-inch diameter tube. The proportional navigation algorithm he developed required the missile to continuously calculate the changing angles between its own position, the target's position, and the predicted intercept point, adjusting its flight path 200 times per second to maintain optimal approach geometry. The breakthrough component was a gyroscopic mirror system that McLean designed during sleepless nights in his China Lake laboratory. The mirror, spinning at 4,000 revolutions per minute, scanned the sky ahead of the missile like a mechanical eye, feeding heat signature information to the guidance computer. When the detector sensed an aircraft's hot exhaust, the system would lock onto that thermal signature and guide the missile toward its target using pure physics and analog electronics. McLean's team worked in near-total secrecy, funded through discretionary research accounts that avoided the attention of Navy bureaucrats who considered the project a waste of resources. They machined components in the China Lake machine shop during off-duty hours, tested electronic circuits in borrowed laboratory space, and conducted initial guidance experiments using surplus rocket motors from World War II programs. The first successful test occurred in September of 1952, when a prototype Sidewinder intercepted a radio-controlled target drone at 15,000 feet altitude. The weapon that emerged from McLean's 9-year development program embodied engineering philosophy that prioritized elegance over complexity. The final design used exactly 14 vacuum tubes compared to the hundreds required by Soviet missile systems. The infrared seeker head weighed less than 10 pounds, but could detect and track aircraft at ranges exceeding 2 miles. Most remarkably, the entire guidance system cost less than $3,000 to manufacture using standard commercial electronics components available from American suppliers. Soviet engineers examining the captured Sidewinder in 1958 could not comprehend the sophistication hidden within components that appeared primitive by their standards. The glass nose cone that Sokolovsky had dismissed as fragile was actually an optical element ground to tolerances measured in wavelengths of infrared light. The simple electronics performed mathematical calculations in real time that would challenge room-sized computers. The expanding rod warhead created a lethal blast pattern 30 feet in diameter, virtually guaranteeing destruction of any aircraft within its engagement envelope. McLean's greatest achievement was not technological but philosophical. He had proven that autonomous weapons could be built using existing technology if engineers abandoned preconceptions about complexity and scale. The Sidewinder succeeded because it solved fundamental problems through innovative thinking rather than brute force engineering. Where Soviet designers added components to achieve performance, McLean's team eliminated unnecessary elements until only essential functions remained. The irony that would eventually transform Soviet missile development was already evident to American intelligence analysts in 1958. The primitive Sidewinder represented the most advanced guidance technology ever deployed in combat, disguised as a simple heat-seeking device that any pilot could operate effectively. Soviet engineers who initially mocked its apparent simplicity would spend the next decade attempting to duplicate manufacturing processes and design philosophies they had never encountered in their own research programs. By the time Sokolovsky received his orders to reverse engineer the American weapon, McLean's team at China Lake was already testing improved variants with liquid nitrogen cooling systems and extended engagement ranges. The technological gap was widening, not closing. The emergency reverse engineering program began on November 1, 1958, with the establishment of a classified facility designated Object 134 in the forests outside Moscow. Sokolovsky assembled a team of 63 specialists drawn from across the Soviet aerospace industry, metallurgists from the Tupolev Design Bureau, electronics engineers from research institutes in Leningrad, and optical specialists who had previously worked on satellite reconnaissance systems. Their mission parameters were unprecedented in Soviet weapons development, complete technological replication of a foreign missile system within 24 months. Vladimir Zvigintsev arrived at Object 134 carrying a leather briefcase containing spectrographic analysis reports that would define the program's initial phase. His examination of the Sidewinder's components had revealed manufacturing techniques that challenged fundamental assumptions about Soviet industrial capability. The American missile's aluminum alloy fins displayed surface finish quality typically associated with precision optical instruments rather than military ordnance. More disturbing, the electronic components showed manufacturing tolerances that exceeded anything produced by Soviet facilities, despite appearing to be standard commercial parts rather than specialized military equipment. The first major obstacle emerged during attempts to reverse engineer the infrared detector assembly. Soviet engineers could identify the lead sulfide crystal technology and understood the basic principles of infrared detection, but replicating the American manufacturing process proved impossible with existing Soviet industrial equipment. The detector required crystal growth techniques that maintained perfect atomic structure across surfaces measured in square millimeters, with contamination levels below parts per million. Soviet semiconductor facilities, designed for producing vacuum tubes and early transistors, lacked the environmental controls necessary to achieve American quality standards. Zvigintsev spent 18-hour days in the metallurgy laboratory, attempting to duplicate the Sidewinder's gyroscopic mirror mechanism. The component weighed exactly 47 grams and spun at 4,000 revolutions per minute while maintaining rotational stability measured in fractions of degrees. American engineers had achieved this performance using bearing assemblies manufactured to tolerances that Soviet precision machinery could not consistently reproduce. Each failed prototype revealed additional layers of complexity hidden within components that appeared deceptively simple. The proportional navigation electronics presented even greater challenges. Soviet engineers could trace the circuit pathways and identify individual components, but understanding the guidance algorithms required mathematical analysis that consumed months of research time. The American system performed calculations that Soviet computers could replicate only through programs requiring hundreds of lines of code, yet the Sidewinder accomplished identical results using analog circuits built from off-the-shelf electronic parts. The implications suggested that American commercial electronics manufacturing had advanced far beyond Soviet military technology. By spring of 1959, Sokolovsky's team had achieved their first breakthrough. Soviet technicians successfully manufactured a lead sulfide detector that functioned at -80 degrees Fahrenheit, cooling the crystal using a nitrogen gas system reverse-engineered from American specifications. Initial laboratory tests confirmed that their detector could sense heat signatures from distances exceeding 1 mile, matching the performance specifications documented in captured American technical manuals. The cooling system itself represented a masterpiece of American engineering efficiency. Soviet missile designers had assumed that cryogenic temperatures required complex refrigeration equipment weighing hundreds of pounds. The Sidewinder achieved identical cooling performance using a simple nitrogen expansion system that weighed less than 5 pounds and operated without external power sources. American engineers had solved thermal management problems through innovative design rather than brute force engineering, demonstrating technological philosophy that prioritized elegance over complexity. Progress accelerated through the summer months as Soviet engineers gradually mastered American manufacturing techniques. The roller-on controls system, initially dismissed as primitive, revealed sophisticated aerodynamic principles that had never been explored in Soviet research programs. These miniature gyroscopes provided flight stability through pure mechanical physics, eliminating the need for electronic control systems that added weight and complexity to Soviet missiles. When Soviet technicians finally built functional roller-ons using reverse-engineered specifications, test results confirmed performance characteristics that exceeded their most optimistic projections. The guidance computer presented the final major engineering challenge. Soviet electronics specialists had identified every component and traced every circuit connection, but replicating the system's real-time performance required manufacturing capabilities that pushed Soviet industry to its absolute limits. The American design used transistors and resistors built to specifications that demanded quality control procedures unknown in Soviet electronics factories. Each component needed to perform within narrow tolerances under conditions of extreme acceleration, temperature variation, and electromagnetic interference. Intelligence reports arriving at Object 134 during late 1959 provided disturbing context for their engineering efforts. American test facilities were already evaluating improved Sidewinder variants designated AIM-9D, featuring liquid nitrogen cooling systems and seeker heads with double the detection range of the original model. While Soviet engineers struggled to duplicate 1952 American technology, the inventors were advancing toward capabilities that would render their reverse engineering program obsolete before completion. Despite these strategic pressures, Soviet technicians achieved their first complete prototype in October of 1959. The R-3S missile measured exactly 9 feet in length and weighed 91 pounds, matching American specifications within acceptable tolerances. Laboratory tests confirmed that their infrared seeker could lock onto target heat signatures, their nitrogen cooling system maintained operating temperatures, and their guidance electronics functioned according to proportional navigation principles reverse-engineered from American designs. The moment of vindication came during initial flight tests at a classified range in Kazakhstan. Soviet test pilots fired R-3S prototypes at radio-controlled target drones, achieving intercepts at ranges exceeding 2 kilometers. The missiles tracked targets through evasive maneuvers, demonstrated autonomous guidance capabilities, and functioned exactly as American technical documentation had promised. Sokolovsky transmitted enthusiastic progress reports to Moscow, confirming that Soviet engineers had successfully duplicated the world's most advanced air-to-air missile. Yet even as Soviet leadership celebrated their technological achievement, troubling performance data was accumulating in classified test reports. The R-3S missiles required 22 seconds to acquire and lock onto target signatures, compared to 11 seconds documented for American Sidewinders. Soviet manufacturing tolerances, despite representing the pinnacle of their industrial capability, consistently produced components that performed marginally worse than their American counterparts. They had successfully copied the hardware, but somehow failed to match the performance. The first live-fire exercises at Kapustin Yar in March of 1960 revealed the catastrophic gap between Soviet expectations and battlefield reality. Major Yuri Petrov, the test pilot selected to evaluate R-3S combat effectiveness, climbed into his MiG-19 fighter carrying 2 prototype missiles that represented 3 years of intensive reverse engineering effort. His target was a LA-17 target drone flying predictable patterns at 20,000 feet altitude, simulating the easiest possible engagement scenario for infrared-guided weapons. Petrov achieved radar contact with the target at 8 kilometers range and immediately began the engagement sequence that Soviet engineers had copied from captured American technical manuals. The R-3S seeker head activated automatically, its lead sulfide detector cooling to operational temperature while the gyroscopic mirror began scanning for heat signatures. According to American documentation, the Sidewinder required approximately 11 seconds to lock onto targets under identical conditions. Petrov waited, listening for the audio tone that would indicate successful target acquisition. 22 seconds elapsed before the distinctive warbling sound filled his headphones, confirming that the R-3S had finally detected and locked onto the target drone. By that time, the engagement window had nearly closed. In actual combat, enemy pilots would have detected the threat and begun evasive maneuvers that could break infrared lock-on. Petrov fired both missiles anyway, watching their white exhaust trails streak toward the La-17. One missile intercepted successfully. The other lost target lock during a gentle turn and exploded harmlessly in empty sky. The test results devastated Soviet confidence in their reverse engineering program. Detailed analysis revealed that R-3S missiles consistently required twice as much time to acquire targets compared to American Sidewinders, reducing their combat effectiveness to marginal utility. Soviet pilots would need perfect positioning and cooperative targets to achieve successful engagements. The performance gap meant that American fighters armed with authentic Sidewinders would maintain decisive tactical advantages over Soviet aircraft carrying R-3S copies. Zvyagintsev metallurgical analysis identified the root cause of their performance problems. Soviet manufacturing equipment, despite representing the finest precision machinery available in the Warsaw Pact, could not consistently achieve the surface finish quality and dimensional tolerances that American commercial suppliers delivered as standard products. The gyroscopic mirror assemblies that Soviet technicians produced with extraordinary effort were inferior to components that American manufacturers stamped out by the thousands using automated production lines. More fundamentally, Soviet engineers discovered that successful reverse engineering required understanding not just individual components, but entire manufacturing ecosystems. The American Sidewinder succeeded because it was designed around capabilities that existed throughout American commercial industry. Standard electronic components purchased from civilian suppliers met specifications that exceeded Soviet military requirements. Ball bearings manufactured for American automobiles provided precision that Soviet aerospace facilities struggled to replicate. The missile's elegance emerged from a technological infrastructure that simply did not exist in the Soviet Union. Intelligence reports arriving from Western sources during 1960 provided increasingly alarming context for Soviet weapons development efforts. American test pilots at Edwards Air Force Base were achieving 80% hit probabilities with improved AIM-9 Sidewinders, while NATO air forces received production missiles that consistently outperformed Soviet prototypes. The strategic implications were becoming undeniable. Soviet air defense doctrine was based on technological assumptions that American innovation had rendered obsolete. The captured American documents that had enabled Soviet reverse engineering efforts now revealed their most disturbing secret. Technical specifications for Sidewinder components listed part numbers and supplier information for hundreds of commercial electronics manufacturers. Soviet intelligence officers realized that the military technology they had been desperately trying to copy was actually assembled from standard American commercial products available to any customer with sufficient funding. The sophisticated guidance computer that challenged Soviet engineering capabilities could be purchased from civilian electronic suppliers and assembled in any reasonably equipped machine shop. This revelation forced Sokolovsky to confront the possibility that Soviet technological philosophy was fundamentally flawed. His team had approached reverse engineering as a military research program, assuming that advanced weapons required specialized development facilities and classified manufacturing techniques. American engineers had achieved superior results by adapting civilian technology for military applications. Leveraging commercial innovation rather than attempting to develop everything from scratch within government laboratories. By late 1960, Soviet test results confirmed the strategic reality that military leadership had refused to acknowledge. R-3S missiles achieved 45% hit probabilities under optimal conditions, compared to documented American performance exceeding 80% with production Sidewinders. The gap was widening rather than closing, as American manufacturers continued improving their weapons while Soviet engineers struggled to duplicate obsolescent technology. The most devastating intelligence assessment arrived in October of 1961 through classified channels that Sokolovsky was not authorized to access, but learned about through informal conversations with colleagues in other programs. American test pilots were evaluating AIM-9L variants with all-aspect engagement capability, meaning they could attack targets from any direction rather than requiring tail-chase geometry. Soviet R-3S missiles could engage only targets flying directly away from the launching aircraft, a tactical limitation that would make them virtually useless against maneuvering opponents. Captain Boris Volynov, the most experienced test pilot in the R-3S evaluation program, submitted his final combat assessment in November of 1961. His classified report would later be released during post-Cold War declassification programs, revealing the moment when Soviet confidence completely collapsed. American pilots achieved target lock in 8 seconds. Soviet pilots required 22 seconds for identical engagement. American missiles track maneuvering targets through defensive turns. Soviet missiles lose lock during moderate evasion. Combat Effectiveness Assessment. R-3S missiles suitable only against non-maneuvering targets under optimal conditions. The strategic conclusion was inescapable. Soviet engineers had spent 3 years and millions of rubles creating an inferior copy of a weapon that American manufacturers were already replacing with more advanced variants. They had learned to replicate American technology, but they had not learned to innovate at American speed. The industrial infrastructure that made American success possible could not be reverse-engineered through analysis of individual components. Most crushing of all was the realization that American engineers were releasing improved Sidewinder variants faster than Soviet teams could copy the original versions. The technological race was not merely lost, it was becoming hopeless. The classified memorandum that Sokolovsky submitted to Soviet leadership in January of 1962 represented the most honest technical assessment ever written by a senior weapons engineer in the Warsaw Pact. Typed on official letterhead and stamped with security classifications that would keep it hidden for 33 years, the document acknowledged what no Soviet official had been willing to admit publicly. American technological superiority was not temporary or accidental, but systematic and accelerating. The Sidewinder missile was to us a university offering a course in missile construction technology, which has upgraded our engineering education and updated our approach to production of future missiles, Sokolovsky wrote in carefully diplomatic language that masked a revolutionary conclusion. Soviet engineers had not merely copied an American weapon, they had been forced to abandon fundamental assumptions about how advanced technology should be developed, manufactured, and deployed. The paradigm shift began with Sokolovsky's decision to reverse-engineer American manufacturing philosophy rather than simply replicating American components. Soviet weapons development had always prioritized complex systems that demonstrated technological sophistication through elaborate engineering solutions. American designers achieved superior performance through elegant simplicity, using commercial components and standardized manufacturing processes that emphasized reliability over impressive complexity. By spring of 1962, Soviet missile programs were quietly adopting American design principles throughout their development pipeline. The R-13M missile, designated as the official successor to the failed R-3S program, incorporated infrared homing technology as its primary guidance system rather than the beam-riding methods that had dominated Soviet doctrine for 15 years. More significantly, Soviet engineers began designing weapons around commercially available components rather than developing specialized military electronics from scratch. The transformation extended beyond technical specifications to fundamental changes in Soviet industrial organization. Weapons factories that had operated as isolated facilities producing every component internally began establishing supplier relationships with civilian electronics manufacturers. Quality control procedures borrowed from American commercial standards replaced Soviet military specifications that had emphasized theoretical performance over practical reliability. The result was a gradual convergence toward American manufacturing methods that Soviet leadership never officially acknowledged but quietly encouraged through budget allocations and personnel assignments. Intelligence reports from Western sources confirmed that the technological gap was stabilizing rather than widening for the first time since the 1950s. Soviet R-13M missiles entering service in 1965 achieved target acquisition times of 12 seconds, compared to 8 seconds, for contemporary American AIM-9G variants. The performance difference remained significant, but it was no longer catastrophic. Soviet pilots could engage American aircraft on nearly equal terms, provided they achieved favorable tactical positioning. The strategic implications became apparent during conflicts throughout the 1960s as Soviet-supplied air forces began achieving combat results that matched American-equipped opponents. North Vietnamese pilots flying MiG-21 fighters armed with R-3S and R-13M missiles shot down American F-4 Phantoms over Hanoi, proving that Soviet reverse engineering efforts had produced weapons capable of challenging American air superiority. The technological revolution that began with one captured Sidewinder had transformed the entire balance of aerial warfare. Production statistics revealed the ultimate scope of Soviet adaptation to American innovation. By 1967, Soviet factories had manufactured more than 70,000 R-3S and R-13M missiles, making them the most widely deployed air-to-air weapons in Warsaw Pact service. Export versions equipped the air forces of 28 nations, from Cuba to North Korea, spreading American technological principles throughout the communist world under Soviet designations and manufacturing stamps. The human cost of technological transformation became visible in individual careers that reflected broader institutional changes. Zvягintsev, whose metallurgical expertise had been essential to the reverse engineering program, was promoted to deputy director of the entire Soviet missile development complex. His success in duplicating American manufacturing techniques had demonstrated that Soviet industry could adapt to foreign technological standards when properly motivated and resourced. The lesson was applied to subsequent programs targeting American radar systems, electronic warfare equipment, and satellite technology. More personally, Sokolovsky discovered that his reputation as the engineer who had conquered American missile technology opened doors throughout the Soviet aerospace establishment. By 1965, he was directing research programs that extended far beyond the original Sidewinder project, overseeing efforts to reverse engineer American guidance systems for ballistic missiles, air defense weapons, and spacecraft navigation equipment. His career trajectory illustrated how individual technical achievements could reshape entire institutional cultures. The ironic vindication came through conversations that would have been impossible during the height of Cold War tensions. Alexei Tupolev, son of the legendary aircraft designer and himself a senior engineer in the Soviet aviation industry, spoke with remarkable candor during a diplomatic reception in 1967 attended by American aerospace representatives. "Your Sidewinder saved us 5 years of development time and millions of rubles," he privately admitted to a Boeing executive. "We learned more from one captured missile than from 10 years of our own research." The strategic balance that emerged by the end of the 1960s reflected technological convergence rather than American dominance or Soviet inferiority. Both sides possessed air-to-air missiles capable of engaging targets at ranges exceeding 3 kilometers. Both used infrared homing systems that functioned autonomously after launch, and both had adopted fire-and-forget tactics that eliminated the need for ground-based guidance systems. The Sidewinder's technological principles had become universal standards for modern aerial warfare, yet the fundamental lesson of the reverse engineering program extended beyond specific weapon systems to broader questions about innovation, manufacturing capability, and technological leadership. Soviet engineers had succeeded in copying American hardware, but they had never matched American innovation speed or commercial adaptability. The industrial infrastructure that made American weapons development possible remained uniquely American, rooted in commercial competition and civilian technological advancement that could not be replicated through government planning. The final assessment appeared in declassified Soviet documents released during the 1990s. Revealing the long-term impact of one captured missile on an entire military establishment. modern Russian air-to-air missiles, from the R-73 to the R-77, still employed proportional navigation algorithms first developed by William McLean at China Lake in 1952. The technological revolution that began with Soviet laughter at American primitive simplicity had become the foundation for every heat-seeking weapon in the world.